So now let's try to study about the polarization of the EM wave. So you must heard about this word frequently when you read the literature in the biology or in the chemistry. So in physics, how we define the polarization of the EM wave is that it is the directions of the electric field, or I should say that the direction of the vibration of the electric field. So let's take a look about the figure A here. Now the EM wave is propagating along the positive x directions, and we know that the electric field should be perpendicular to the x. So now, if you have the electric field oscillate along the z directions, then we claim that this EM wave is polarized in the z directions. So this z means positive and negative z, so they will oscillate. So this is when we define and claim that or tell people what is the polarization of the EM wave, we use the electric field as a reference, not the B field. But you agree that once we determine the direction of the wave propagation and the direction of the E field, then you automatically use the right-hand rule. You can find out the direction of the B field. However, the XYZ coordinate is simply a coordinate you choose. So the electric field can still oscillate perpendicular to the direction of wave propagation, but not in the Z direction anymore. So for example, now this is the direction of the polarization of the electric field. Now it is the 60 degree above the y-axis. So we will say this one is still polarized, but the polarization of the two waves are different. So now this is a definition of the polarization of the EM wave. So let's try to study a little bit more details. So if you have a polarized wave, EM wave, it simply means that the electric field are all oscillating in the same direction, all point to the same directions, or to the z, or to the negative z. So this is what we just defined in the previous slides. However, you can also have an unpolarized light. And what do we mean by unpolarized light? It means that the electric field is in the random directions. So I should be very careful when I say the random directions. So when I say random, which means they don't only oscillate into one particular directions, but no matter which direction they oscillate, they all perpendicular to the wave propagation. So for example, if you oscillate into these directions, they are perpendicular to the wave propagation, but if you oscillate along this direction, which also is perpendicular to the wave propagation, but if during the propagation of the electric field, they don't point to a unique directions, then we claim this light is unpolarized. So not all the EM wave is polarized. So we should be very careful. So now, if you have an unpolarized beam or the light, how can you make it polarized? So the trick is you have a device called the polarizer, and you can control the so-called transmission axis. So what do we mean by the transmission axis? It means that when the EM wave propagate and hit on the polarizers, only the electric field in these directions can be propagated through. All the other direction of the electric field will be blocked. So which means they choose a particular component of the electric field to pass through. So which means that at passing through the polarizers, the electric field will only have one direction left. Then originally you have unpolarized EM wave. After that, you have a polarized EM wave. So polarizer is a very important approach to make an unpolarized beam polarized. However, you can see that the magnitude originally have the intensity I0, but after all the wave passing through the polarizers, the intensity is no longer the same. So the reason is because the intensity originally is distributed equally among all the directions of the electric field, but now only one direction is allowed. So not all the intensity was propagated and transmitted through. So this is the so-called Mueller's law. So they tells you that the intensity of the light after passing through the polarizers, it will be proportional to the original intensity multiplied by the cosine theta square. So what is the cosine theta? So let's take a look about this diagram. It is the angle between the transmission axis and the original direction of the electric field propagated through. And for sure, here you have random direction, so the theta will depend on which one is blocked. Yeah? So now, you will see apparently, because cosine theta is more than 1 or equal to 1, so the intensity of the transmitted beam definitely will be smaller than original intensity. And the light exists well polarized in the direction of polarizer, as we just mentioned. And how did you calculate the I0? So I0 is through the equation here. So this is the electric field ran in the random direction before passing through the polarizers. So how about this particular case? So if you have a polarizers passing through, if you have this EM wave, originally it is vertically polarized. So it is not in the random directions. And you put a polarizers which the transmission axis has a theta compared with the vertical directions. So originally the intensity of the EM wave is I0. But after passing through the polarizer, only the component in this direction is allowed. So you will find out after that the transmitted light is polarized in this direction, but now the intensity is I0 multiplied by the cosine theta, and the theta is the angle here. So you can also consider it is because of the electric field is decomposed into the component parallel to this transmission axis and the other component which is perpendicular to that. So only the component which is parallel to the transmission axis can passing through. So therefore now the intensity I0 is energy density multiplied by C. This is in general true no matter for which case. But originally now, if you have the electric field E, then after you passing through the polarizers, you will have I0 cosine theta. So how about the case if you have unpolarized beam? So now this is the case you will see. If you have unpolarized one, so you will ask then which one I should use to determine the angle of theta. So the answer is you should not use any one of them for theta. What you should do is, because it is randomly pointed to all the directions, so you are going to find the average value for the cosine theta square. So in that case, no matter what kind of theta it point to compared with the transmission axis, when you sum all the value and get the average value is 1/2. So now, if you originally have an unpolarized beam and passing through a polarizers, then the intensity after the passing through is half of the original intensity. And the reason why you got half is because the average of the cosine theta is 1/2. So now these two slides will show you the two most the general result today. First, if U originally is polarized, then when you passing through the polarizers, what will be the result? You simply using this result. And if U originally is unpolarized and passing through the polarizers, you still have to use this result, but now this value should be the average value, so you can simply just apply the 1/2 factor there. So now, if you put two polarizers, so the first one is called the polarizer, and second one is still the polarizer, but people give a different name for that. It is called the analyzer. So they are all intrinsically just the polarizers. Now, if you originally have an unpolarized beam with intensity I0, after passing through the first polarizers, then you will become half of the original intensity, as this is the result we just learned before. And now this one will become vertically polarized. And now the second polarizers, the transmission axis, has an angle compared with the vertical directions. So therefore, the final transmitted beam is 1/2 of I0 multiplied by the cosine theta. So that's the reason that if you now have the two polarizers, the final intensity is this one. And the theta here is determined by this analyzer. So if you try to use the thing which can be visualized, so the polarizer, what they play is that if you have the light source, you can consider they try to put some barrier and only some particular point can passing through, yeah? So let's use the example you can find in your daily life. If you have the string vibrate, and this is the gap you can produce, so you can see that you allow an oscillation of the string in the vertical directions. So you can treat this one as a polarizer. So the vibration of the string can still passing through. So this is basically what happens here. However, for the first polarizer now, if it is vertical, so the string of the wire still can passing through. But if you put the second polarizer, which is in the parallel directions, and when the string vibrate and try to passing through, the string can no longer vibrate along the vertical directions, so it will simply become 0. So here is a very important message is that if you put two adjacent polarizers and the directions are perpendicular to each other, then what will happen is that no matter originally how big the intensity it will be, the intensity of the transmitted wave will become simply 0, because there's no way for the vertical component to passing through the vertical gap or the polarizer.